Welcome to Chem Help ASAP. In previous videos we've talked about resonance, and we've really applied resonance in only one situation. And there are actually three scenarios where we will encounter resonance. So I want to review the first one and then talk about the other two. So we have on the screen the three scenarios or three situations or three templates from which we'll apply resonance. The first one is familiar to us. If you've been watching this playlist in order, we have a double bond next to an atom with a lone pair, and this is how we move the electrons. Here's an example of this, and I forgot a negative charge. It is, here's a carboxylated, deprotonated carboxylic acid, and we can shift the electron density, delocalize the charge to get this alternate Lewis representation. These are both equal contributors in the picture since they're both O- and the bonds are all the same. The great thing about this top situation is when you draw these alternate resonance forms, these alternate Lewis dot structure representations of your molecule, they tend to have full octets. So we satisfy the octet rule. And of course, that's the number one rule when writing a Lewis dot structure. So we tend to draw good resonance forms. Not all scenarios for resonance are so good. So in the second example, as it turns out, anytime you have a pi bond, you can break that pi bond. And as we've shown here, we can push the electrons onto one atom or the other. We could have pushed them on B instead of pushing them onto A. And that's a new Lewis representation. And when would we see this? Well, here's a specific example. This is the simplest aldehyde. It's called formaldehyde. And we could break this CO pi bond, put the electrons up onto the oxygen, and we get this structure. That is a new Lewis representation. That is a resonance form. However, the resonance form we draw from simply breaking bonds tends to give us non-octet rule compliant structures. This carbon now has only 6 electrons in its valence shell. It doesn't satisfy the octet rule. So the resonance forms that we tend to draw tend to be minor contributors relative to the original structure. Doesn't mean they're worthless, it just means they're minor contributors. In the third situation, we tend to encounter this almost exclusively just with carbocations. So we have a carbon. That carbon has a formal charge. It has it's open shell, doesn't satisfy the octet rule. It's sp2 hybridized, which means it has a vacant p orbital on it. Now we need that p orbital to do the resonance. And we can break this carbon-carbon double bond and move it to the other side and shift its position. We can delocalize that positive charge if we have a double bond next door. This is far less common than these top two, but we will encounter it later. And so the resonance is actually an important way that we can stabilize carbocations. So I want to mention that for completeness, but really, whereas almost all of our action for resonance, it's going to be right here with number one. But we will see number two a little bit. So these are the three situations in which we will encounter resonance in organic chemistry typically.